Welcome back. In this lecture, we will be reviewing the second law of thermodynamics. As we know that many processes are natural processes, and some processes by default will not occur unless we make use of external devices. So, there is a certain direction of the process, and this is basically governed by the laws of thermodynamics. So, in order to have some processes to occur, we need to make sure that the first law and the second law satisfies. Okay. So, in other words, the direction of a process can take place is given by the second law of thermodynamics. Okay. The first law of thermodynamics do not put any restriction on the direction of the process. So, it cannot ensure that the process can actually occur, and changing the direction or the direction itself is controlled by the second law of thermodynamics. Hence, changing the direction would mean violating the second law. Okay. So, as I said, a process can occur only when the first and second law are satisfied. So, let us just take an example which is well known to us. For example, you have a stirrer in a container having water, and while we rotate this shaft, which means that we are doing certain work, because of that there is a heat being generated. That means the work is getting converted into heat. On the other hand, if you apply heat, you cannot rotate the shaft, or this will not rotate, and thus the process of heat directly to work is not spontaneous. So, there is a direction to the process, the first where the work automatically gets converted into heat, whereas the opposite process is not feasible. Okay. That means the reverse is not true. So, in order to convert heat to work, a special device is being developed, that is we call it heat engine. So, let me just summarize what or let me just quickly go through the heat engine concept. So, heat engine basically consists of many devices here within this circle, and it operates on a cycle. It receives heat from a high temperature source Q in, converts certain part of that as W net out, and rejects certain amount to a low temperature sink in order to have a complete cycle. Okay. And the fluid which is used as a part of the heat engine is we call it working fluid. So, it could be water, for example, in steam power plant water is used, or it could be gas, that would be the case of let us say a gas turbine or car engine, which is a part of internal combustion engine, which do not follow precisely the thermodynamic cycle, but it follows a mechanical cycle. So, considering the heat engine here, as you can see, it consists of 4 basic units: the boiler, turbine, condenser and pump, and this is the direction. Okay. It goes in this way. It takes the heat, heats up the fluid, which is in this case water for the steam power plant, to a very high pressure, expands in the turbine to a low pressure, and because of expansion it rotates the shaft, getting the work out. At low pressure, it rejects heat from the vapor, it gets condensed to the liquid, liquid gets pumped back to the pressure of the boiler, and this continues in a cycle. So, if you do a simple balance here, you have this work out, which is a W out minus W in, okay, and then this must be equated to the net heat in also. So, that means from based on the first law of thermodynamics, W net out should be equal to Q in minus Q out, okay, and this is a closed system. That means there is no mass enters and exits the system. Okay, and the other thing which we have assumed, because delta U of the cycle is 0 because it is a cyclic process. Okay. So, how do you define the efficiency of a heat engine? As I said that not all a part of the heat gets converted to the work, certain amount of the Q in gets converted into the work and the rest are rejected as Q out. So, we defined that efficiency of the heat engine in terms of net work out divided by total heat in. In other words, eta is W net out divided by Q in, or you can write it in this form. So, which essentially means that you may have the source and sink for two different engines same, but it may have different efficiency, because that may depend on internal part of the internal part of this heat engine device, heat engine overall. That means there are four devices for a generic heat engine, and it may depend on the efficiency of individual devices. Okay, but the eta in clearly depends on W net out, and hence you can work on the devices in order to increase the efficiency for a given source and sink. Now, in addition to the heat engine, you have other cyclic devices, and these are refrigerant and heat pumps. Particularly refrigerant and heat pumps, they operate at a high temperature reservoir and low temperature reservoir. So, in addition to heat engine, refrigerators and heat pumps, they are also part of the cyclic devices which operates at high temperature reservoir and low temperature reservoir. So, in general we can generalize that QH is the magnitude of a heat transfer between the cyclic device and high temperature medium at temperature TH, okay. And similarly QL is the magnitude of heat transfer between the cyclic device and a low temperature reservoir, okay. And W net out would be simply QH minus QL, both are positive, okay. So, this is a generic definition as far as the reservoir is concerned for all these cyclic devices, okay. And eta will be always less than 1. So, this brings to the second law of thermodynamic statements. So, for heat engine we make use of Kelvin Planck statement, which says that it is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. This is equivalent of saying that QL would be 0, which would mean that it will violate this second law or violate the Kelvin Planck statements of the second law. So, in other words, eta can never be 1, okay. Now, in addition to heat engine, if you want to transfer heat from a low temperature to the high temperature, which is not a natural process, you need to use a different device which we call it refrigerator, okay. Or refrigerator basically also have many components in it, okay. This is a example of vapor compression refrigeration cycle, where you have condenser, compressor, evaporator and expansion valve, okay. And its purpose is to maintain the refrigeration space at a certain temperature, let us say TL, okay. This works also in the cyclic device, and the fluid which is used in this device is called refrigerants, okay. So, this is the typical one. So, instead of the path for heat engines, which is in this direction, this is anti-clockwise for the case of refrigerant cycles, or for the case of this cycle. So, the fluid gets evaporated, further compressed and condensed, and basically expansion valve is used to expand, and the heat is being rejected to the kitchen air, okay, here, and the heat is being extracted from the refrigerant space to maintain a certain temperature TL. Okay. To define efficiency, we use the coefficient of performance, which is nothing but is a ratio of the desired output and the required input. For the case of a refrigerator, what is the desired output? It is the amount of the heat which is being released from the cold space in order to maintain the temperature. So, QL becomes the desired output, and divided by the required input is the W net in. Now, for the case of a heat pump, the purpose is to maintain the environment of the room at a certain temperature TH, and thus for the case of the heat pump, the desired output is going to be QH. So, the case of the heat pump, the coefficient of performance would be QH divided by W net in. So, this is the generic idea behind these cyclic devices, okay. And one can also rewrite this in this form, because we know that from the first law analysis that W net in is QH minus QL. You can plug in this equation and you can get CUP in this form, okay. Now, as we also mentioned about the statements of the second law of thermodynamics, Canning-Planck clearly statement relates to the heat engine, whereas for the case of refrigeration devices, we make use of Clausius statement, which is basically that it is impossible to construct a device that operates in a cycle and produces no effect other than transfer of heat from a lower temperature body to a high temperature body. So, it simply means that W in cannot be 0 for the case of refrigerator. So, such scenario violates the Clausius statement of the second law. Okay. All right. Now, so having briefly reviewed these aspects of the second law, we will also talk about the reversible and irreversible process. Now, what is the highest efficiency for a heat engine? Okay. And as we know that eta can never be 1, or we cannot achieve 100% efficiency, but then still the question is that we would like to theoretically attain highest efficiency in order to consider that as a yardstick for our designs. So, what would be the case for highest efficiency? That will be when the device operates on a reversible process, or paths are considered to be reversible. So, let us review the reversible process. It is basically a process that can be reversed without leaving any trace on the surrounding, which essentially means that you can bring back the system. Okay, the process is such that you, once the process occurred in such a way that you can bring back the system to the original state, and similarly you can also bring back the surrounding to the original state without affecting overall any trace changes, or that means you are bringing the system and surrounding back to the original states. Now, this is difficult to imagine though, but we can consider a case of expansion and compression of a system where we operate in such a fashion that it is so slow that external and internal is all the time at equilibrium with a very small change in pressure, for example, and thus the forward and the reverse process do not affect the overall systems after it returns back to the original state. Okay. Or similarly, you can also consider, let us say, frictionless pendulum from going to this point and coming back do not affect the surrounding as well as the system here. So, this is basically nothing but idealization. Okay. So, let me again summarize reversible process. It is a process that can be reversed without leaving any trace on the surrounding. That means, both the system and the surrounding are returned to their initial state at the end of the reverse process. Okay. However, irreversible processes are of course widespread. An example of such a process could be considered in unconstrained expansion. So, you have a container containing gas at very high pressure separated from this low pressure subsystem with by a membrane which gets ruptured, and upon ruptured the gas flows from this part to this part and fills the entire volume. Now, if you would like to return this back to the original state, we must try to push this gas from here onward, okay, using some kind of a piston. Now, while we push back, the pressure will increase and leading to increase in the temperature, but if you want to return back to the original temperature, you have to take it out the heat. So, you are doing a work, and as well as you have to remove the heat. In order to make sure that the system plus surrounding returns back to the original state, you have to convert all the heat which you have taken out to the work, okay, which essentially means you are trying to violate the second law, and that is not feasible in this case. Okay, so, this kind of a case would be irreversible process. So, what is the cause for the irreversibility? These are the friction, unrestrained expansion, mixing of two fluids, heat transfer across a finite temperature difference, okay, and electrical resistance. Now, for example, heat transfer across a finite temperature difference means the heat transfer will be very fast. On the other hand, when the delta T between the system and surrounding is very small, then the system is very slow in transferring the heat, and that is what we assume as far as the reversible process is concerned. Okay. Beside this in a reversible process, so the one which we have talked about is basically total reversible process here. Okay. In addition, we also consider when the system is internally reversible. In such case, what we assume that system can be brought to the original state, however the surrounding may contain all the irreversibilities. So, in those kind of cases we will call as internally reversible, okay, where the surrounding may have, from the system to surrounding may have finite temperature difference, but within the system we will consider that everything is reversible. So, those are the systems or those cases, particularly internal reversible, are the ones which we are going to consider most of the time when we discuss the problem. Okay, so now I move on to a particular case where we make use of Carnot cycle. Okay. Now, heat engine, as I said, depends on the network as far as the efficiency is concerned, and we would like to increase the efficiency of the heat engine, and that can be done when we maximize the net work. Okay. So, maximum work can be achieved when the process is reversible. Okay. So, reversible cycle provide upper limits on the performance of the real cycle. Okay. Now, this is something which becomes a yardstick for our design. So, one of the reversible cycle was proposed by Carnot. Okay. It consists of 4 reversible processes, and 2 of them are isothermal and 2 of them are adiabatic. So, is considered a gas, okay, in which the first let us say the first state to second state is being considered, where this is a reversible isothermal expansion,